Hello, welcome to the sixth class of the ISSS session of computational physics with Python. So let us get started. First, let me start by sharing my screen, and we'll start off from what we have left. From where we have left last day, we were stuck at solving the transcendental equation for Wien's displacement law. So I have had the time to get back to it and look at it more closely, and hopefully we'll be able to solve this today and move on to complete the other questions of this set. So, okay, so let's me share the screen. And as usual, please feel free to stop me whenever you are stuck, and I would be happy to answer your questions. Okay, so this is the code where we have left off roughly. This is the place. And I think where we were stuck is this problematic thing of exponents. While exponents are really good in terms of analytic simplicity, but when you deal with exponents in numerical setting, they can be quite notorious in terms of giving you values which are very large or very small, depending on the value of your exponent, right? So what's happening in here is while we are trying to optimize for the solution, this expression inside the exponent is becoming too large, and therefore this is giving rise to some undefined numerical errors. And this is exactly what we are happening, or the problem which we are facing in here. Okay, so we will be trying to solve that, and let's see how far we succeed. Okay, so the idea here is, but the basic idea behind this kind of thing that we are doing remains the same, and it's not a problem that we have in the understanding of the code, but the problem lies in the details of how we are implementing it for this specific equation. And this will work perfectly fine for any other equation which is much better behaved than these problematic exponentials. Anyways, so let's see. So the first, we are trying to find out the lambda at max and T. So at what temperature do I have the maximum radiation at any particular temperature? What's the maximum radiation that we have? So we are solving for the lambda max at some particular temperature. And the temperatures we are varying from 1000 to 20,000 Kelvin, right? And that's how we are going to do it. And then we, at every temperature of the black body, we are trying to find out what would be its the peak at which its emission is coming out at, right? So then that depends on the black body spectrum, which has been already given, right? So the peak would be the place where your derivative di d lambda is going to be. So this is di d lambda, right? So di d lambda, just to be more understandable, I have changed L to lambda. So this di d lambda is 0, is where we have the maxima. So that is where we want to find out the root of di d lambda. And that is where we are going to have the temperature maximum. Okay. So sorry, that we're going to have the wavelength maximum at the intensity maxima at that particular wavelength. Okay. This was confusing. Anyways, you get the idea. Okay. So we'll start in here. Count the number of iterations. A is 10 and B is 1000. So that's like 2 wavelengths. And let's take this wavelength, say, in. So while dealing with wavelengths, let's say we take the wavelengths in angstroms, right, or in nanometers. So the say wavelength is in nanometers. So then what we do is, before passing this, we have to convert that to nanometers, right? So let's see, before calling on to these functions, this is A times 1.0 E minus 0.9. This converts to nanometers, and B is also. Right, so this should be in nanometers. This is in nanometers. So we are looking at wavelengths between 10 to 1000 of a nanometer, right? So this is like the wavelength that we are initially guessing, and then we want things to come close to what we are guessing. Okay, so okay, and in fact we can even make it large so that we have a large range. It can be for low temperatures, the wavelength can be very high. So yeah. Okay, so now we see with the intermediate thing, and then we look for this, and then again here we do this. So this again converts the wavelength to nanometers just to find out how much it is. And then here we do something like a delta. So it's 1 plus delta, right? Because we want to find out how much uh, we also have to do this delta in terms of the nanometers, right? So this delta is therefore also in terms of nanometers. So it's wavelength times 1 plus delta, and then it's 1 minus delta. And just to be safe, as I've said, it's always a good idea to do a 1 dot. Although Python most likely will is smart enough to figure this out. And 2 times f times delta, right? So this is roughly the thing. And then we are going to do this. We are going to print max wav, and then we can plot the temperatures as a function of maximum wavelength, right? And see how this is behaving. And then we can go to the next part. So for now, let's have this part commented out. We'll try the next part before. Okay. Right. So here we see that we roughly get more or less the same thing. We are at some trouble at smaller temperatures for sure, but say because at smaller temperatures the wavelength is pretty high, and that can cause trouble again because of the exponent thing. So we can neglect the smaller temperatures for now. So let's start with something like instead of 1, let's start with something like 2.5. Let's just avoid the problematic part. Right. I'm sure there can be better ways of dealing with the problematic part, and that is using the approximation for the exponent. So there is this approximation to the black body function. At one end, it's called the Wien's function, and the other end is called the Rayleigh-Jeans part. So you can use those approximations at the two different extremes, and that will give you better results. But for now, let's not worry about it, and only take a range where the thing is better behaved. And here you see that there is temperature on the x-axis. So let's plot, say, we can, for example, plot 1 over temperature, and then max wavelength is this. So we can do something plt dot x level. Sorry. This is 1 by temperature in Kelvin, and plt dot y label is wavelength in nanometers. All right, and we do this. Right. So now let's see. Okay, so you see this with 1 over temperature and wavelength, I get a straight line. And this shows that there is a linear relationship between lambda and lambda and 1 over t, and this slope of the straight line is going to give you the value of the wind's displacement constant, right? So to get just the value, we can do just lambda times t. So that will be simply we can print. We can do another plot of lambda times t that will give you the wind's displacement constant in terms of nanometers times Kelvin, right? So what we will do is let's have temperature on the x-axis, and we have max wave times temperature, right? And then the y level will be Wind's constant. Wind's constant, right? This is fine. Yep. Okay. You see, it's very close, oscillates, but very close to this value, and the Wind's constant is the units of nanometers times Kelvin. And if you want to see say the average, then you can also write PLT dot title Wind's constant. We can again use S strings just as before. Get rid of this. And we name this we do an pi dot average of this is in terms of nanometers times Kelvin 0.3 E. So let's write it in terms of meters per Kelvin. If this is in meters per Kelvin, then this should be also multiplied by 1.0 E minus 0.9. So this entire thing has to be the Wind's constant, right? In terms of meters per Kelvin, because nanometers is not what we are going to use, just in SI. So let's run this. And you see it's 2.898 times 10 to the minus 3 meters per Kelvin. So let's see. Meters times Kelvin. So let's see what is the value of the Wind's constant if you want to check. Or value of Wind's constant. So it's 0.2.89 times 10 to the minus 3. And what we have got 2.89 times 10 to the minus 3. So this is exactly what we have got. So I think we are fine in terms of finding out the Wind's constant. Let me know if there are any doubts in this part of the question. If not, then we can go to the next part. Okay, so let's then go to the next part of it where we are asked to find out what would be the value of the temperature of the sun when we know that's maximum wavelength comes at around 502 nanometers. So this is the other way around of doing this problem. In a way, we know this already analytically because we know that we have already found out the Wien's constant, right? So analytically, we already know what would be the maximum temperature of the sun. So that's going to be, say, we know 2.898 times 10 times E6 is the value of the Wien's constant in nanometers times Kelvin, right? So if you divide it by the 502 nanometers, then what we are going to get is the temperature of the sun, which is around 6,000 Kelvin, as you can see in here. So this is the result that we expect from that calculation from Wien's constant. And let's see if we try to do the other way around, that we know the maximum wavelength and we want to iterate for and optimize the result to get the temperature. How close do we get to the result that we expect? All right. So we again give it a temperature between A and B from something between 1,000 to 20,000. Rather, we can give it a little bit larger, as we have seen. This is 1,000 is temperature and 20,000 is also temperature. C, and then we go through the same procedure of just dividing one by the other. And then when we call the wavelength, we call the wavelength in here. So we know that it is 502. So it's 1.0 E minus 0.9. So this converts it to nanometers. Right? So we have 502 nanometers. And then now the wavelength remains fixed, and it is the second argument, which is temperature, on which we are trying to find the solution, right? And the place where, again, where dig lambda is maximum, right? So again, the same F, we do the same thing in here, try to find out the temperature, and then we get it for the temperature of the sun. Okay, so let's run the other part of this. And we get the temperature of the sun is 5,800, 5.8. So we can also do something. 5,800 Kelvin. Let's see what else the other print we have. We can just command one, just uncomment this from Wien's displacement. We know we should get around something around 5772. So let's make this 3 just to have a few more decimal places, but it doesn't matter. So yes, you see that we get something which is same as the value that we are getting in here. So we have the Wien's displacement constant, and if we are going the other way around and trying to solve for it, we get the temperature of the sun same as what we expect from the previous part after knowing the value of the Wien's displacement constant. Right. So please let me know if this part is clear or not. Okay. I guess there are no questions. Then we can proceed to the next part of it, which is about the potential well. Okay. So let's see the question once. Mm, yep. So consider a square potential well of width W and height V. Using Schrodinger's equation, set up the equations for allowed energy levels E of a single quantum uh, particle of mass m trapped in the well, or an electron of this mass and V of this, and W equals to 1 nanometers. Write a Python program to calculate the values of the 6 energy levels in electron volts to accuracy of this using the false position method. Right. So we are going to use the regular falsy method or the false position method. So let's first look at what this method is. Right. This is one of the methods for finding out the root of a transcendental equation. So this is how it works. So consider an equation fx equals to 0, right? And here it says, yeah, which contains only one variable, that is x. To find out the real root of the equation, let's open this in this tab so that it's easy for me to go back. This is false position method. Yep. Okay. So to find out the real root, we consider a sufficiently small interval a less than b such that fa and fv will have opposite signs. So exactly what we were doing. And then according to the intermediate value theorem, the root lies in between. So this is very similar to bisection, which we have already done. Now the equation of the chord joining a and b is given like this, where you draw a straight line which joins the a and b points, right? And that's given by this equation. This is also simple. This is just the equation of a straight line. So if you have some, you have fa and fb at x equals to a and x equals to b, right? So you do something like this. So this is nothing but y minus fa by x minus a equals to f minus fa by b minus a. Yeah, this is just a simple estimate for the slope, and then you get the equation of the straight line, right? Then let y equals to 0 be the point of intersection of the chord with the x-axis. So we want the position where fx is going to intersect the x-axis. But we are estimating that with the line, which is with a straight line, but it might not be a straight line. So that is where we are going to converge closer and closer. The idea here is that as our estimates for A and B improve and become closer and closer to the real root, then straight line is a good approximation to a curved line. Okay. So this is what the idea on which it is. This is based on, right? So you can think of this as here, and then we are closing in on A and B and new estimates for A and B, which takes us close to the root, which is actually x3 here. Okay, so this can be simplified to this. Thus the expression x1 equals to this. Also x1 is the root of x at fx1 equals to 0. If x(x1) is not equals to 0, if f of x1 not equals to 0 and if a has opposite signs, then we write the second approximation as this. Similarly, we estimate this and so on. Okay. So then we are going to discard the one root and take the other root depending upon the sign. So this is roughly the idea of regular parsing. So let's try to do this. But before doing that, we have to find out what are the equations that we are looking at, right? So let's find that out. Let me get rid of these. Perhaps this is useful. Since we are dealing with quantum mechanics, perhaps these constants are also useful, and let me get rid of the rest. Okay, so now we are trying to find out the equation. So it turns out if you solve the square rectangular well problem, which obviously is beyond the scope of this thing that I'm covering, and you will get it in like elementary quantum mechanics course as an undergrad in physics. So I'm not going into the detail of it, but I'm just giving you the formula which gives you the estimate for the energy levels in a potential well. So it's a finite potential well. There is also something called an infinite potential well, but that is a bit simpler, but this is also not that bad and difficult. Okay, so let me go back to the question and give you an idea of what's happening in here. So this was question number 7, I guess. Yes. So let's open the info. Okay, so these are the two equations that we are solving. So there are two different types of energy levels that you get depending on the characteristic of the wave function. Sometimes the wave functions are symmetric about x-axis, and sometimes the wave functions that you have are antisymmetric about the x-axis, where x-axis is position. So the wave function as a function of position can be either symmetric or antisymmetric. And then it depends on how you deal with it. Each wave function comes with an eigenvalue, which is the energy of the state. Again, some of these terms can seem a bit foreign, and I do not blame you for it if you have not done a course in quantum mechanics. But nevertheless, this doesn't hinder you from following the numerical methods that we are going to implement for solving the potential, the energy eigenstates or the energy levels in a potential well. Okay. So the one numerical point to note in here is that you can see this is clearly a transcendental equation where we again have to solve for V, right? U naught is given, so you know the mass, you know the size. L is the size of the potential well, M is the mass of the potential well, and H bar is the Planck's constant divided by 2 pi, and V is the depth of the potential well. So everything is known except for V, which is KL over 2, right? And K is related to energy as root 2 m E over H bar, right? So if we are able to find out V, then we are obviously able to find out what is the energy of the quantum state. But as you can see, since tan and cot are involved, if you look at the graphs of tan and cot, so let me open something to plot the thing, just a simple plot of functions. So say I can open Desmos, which is a graphing calculator. Okay, so if you do y equals to tan of x, right, you'll see that it blows up. So at these points where it becomes infinite, right, because tan has this feature of becoming infinite at certain points, right? Similarly, and this although can be straightforward in terms of analytically, we know what's happening, but if you try to implement tan numerically, it becomes a problem. And that is exactly what we would like to avoid in what we are doing. And so would you have for cot. cot is just nothing but 1 over tan x, right? So let's put this in here. And you see, it again, blows up. The places where tan x is 0, you will have cot x, which blows up, and vice versa. So we are going to avoid this tan x and cot x, and instead we can use sines and cos, which are much better behaved, numerically speaking. So if you have, say, sine x, and nowhere does it blow up. So this is much numerically well behaved, and the values remain between -1 and +1. So far, so good, right? So this is the way that we are going to follow it. So now let's have h bar in here, which is h by 2 pi, as I was saying. Pi, we do not need these. Instead, we need electron volts in here. And if I'm not wrong, it's 1.602 e minus 19. If we go off, then we will check once again. Okay, so function 1. So let's call the symmetric function. And this is a function of u, right? Because that's what we are trying to solve. So we will have something like a u. And now let's look at the function. Yeah. So if you rearrange this, you can write this as sine by cos, right? And take the cos on the other side. So you have root under of u naught square. And then you can take square on both sides. That will make you have u naught square. So let's try to solve this. I'll also give you some time while I also work this out to be 100% sure. And I also urge you to work this out and express this in terms of sine and cos. And we can also get rid of square both sides and get rid of the root so that with roots, sometimes you can get negative numbers inside a root, and that can become numerically ill behaved. So we can also get rid of the root. So then what we are going to left with is u naught square minus v square is equals to v square tan square v, right? And then if you do u naught square, you will have v square 1 plus tan square v. Then you will have u naught square is equals to v square sec square v, right? So, and we know sec square v is nothing but cos square v. So this is simple. So you have u naught square minus v square by cos square v is equals to 0. Is what we are going to solve for the first set. The second one, we have u naught square minus v square is equals to v square cot square v. So you have again u naught square is equals to v square 1 plus cot square v is u naught square is equals to v square cosec square v, right? So this will give you u naught square minus v square by sine square v equals to 0. So we are going to solve for the symmetric and the antisymmetric ones. The first one is the symmetric, and the next one is the antisymmetric, right? And these are some minor details, which obviously you don't need to worry about, just for your information. Yeah. So this will be u0 star star 2 u naught square minus v by cos v this square, right? So now let's write what are u naught and v. This is what we are going to return, right? Even then, let's write this in terms of lambda functions. Okay. So if I go look at the symmetric ones, this is v, this is a function of v. V is what we are going to find out, right? And then we have v by u naught square minus v by sine v whole square, right? And then now we are going to find out what is u naught, right? So u naught is going to be ml square over 2h bar squared times v. L is the size of the width is 1 nanometers. U naught. So U0. This is ml square over 2h bar square. M right. And now we are going to find out the mass of the electron. Right. So mass is equals to, I have, it's written in here, 9.1094. E minus 31. So once we have done this, we know everything, right? And then we are going to solve for these transcendental equations, right? So let's try to do that. And if you look at 2h bar ml square 2h bar square times v. There is another times which we are missing, which is a velocity voltage volts. This is about the potential, right? So volt. So the voltage is 20 electron volts, 20 times EV. Let's call it volt, and let's call it volt. So 20 electron volts is the potential. Sorry, is the depth of the potential well. Okay. And we want an accuracy of 10 to the power of minus 3 in electron volts. Okay. So now we are going to use the false positive method, where we choose points which are sufficiently close to on either side. So for that, we choose, let's say, A, which is some value of u, say minus 10. Oops. Choose B is equals to 100. And we are looking for solutions which is within this, right? So let's try to put these values and see what happens. So it's running this code so that these functions get registered. And let's try with the sim of 10, right? Gives you a value is positive, and sim of 100 also positive, and sim of minus 10. So which is okay. So we will try a value of minus 1000 and a plus of 100. Okay. And C is equals to 0. Start with, we'll have 0 iterations. And now we are going to go and depth is going to start with an infinite value, while if is less than tolerance. So this is what we are going to call tolerance, right? So if diff is less than tolerance, we are going to for loop it, or sorry, iterations is less than max iter. So we do max iter equals to, say, 5,000 iterations is what we are going to willing to go max. And once we are in here, we try to find out the values of FA. And let's call this function as F. F is equals to symmetric, right? And F FA times FB is greater than 0, then there will be a same sign. Then you have to print problem, which you do not want. So to start with, you want them to have different signs so that the root is contained within, and then we can use the false position thing, right? So we do an XTMP. This is the temporary value, which we find by regular falsy method. So we do times A times F of B. All right. And then we do minus of B times F of A. And this has to be divided by FB minus FA. Okay, so once we have done this, let's see. Now we are going to compare the value of the function at this point. And I think we not even need C in here. And now we are going to compare F, X, F at XTMP TMP so the difference is okay. So XTMP is this, and now let's find out the difference. Let's calculate the difference. So the difference is here np.sqrt square root of the, or we can just add the absolute values to get from both A and B. So X TMP minus A star star. So we just add in quadrature so that we want the A and B's to be as close as possible, right? And we do np.sqrt square root of this, right? So now once we have done this, we have found out the difference, we calculate f of xtmp, and we see what's the sign of it. If it is sign is positive, then we assign it to A, assuming A is positive, or if it is negative. I mean, the idea here is that whatever the sign of xtmp, f of xtmp matches with f of A, then A will be replaced by xtmp. If the value or sign of f of xtmp matches with f of B, then B will be replaced by xtmp. So we took an f of B, f of A, right? And if this is greater than 0, that means xtmp and f of A has the same sign, right? So then we replace A equals to xt underscore tmp. Else we know that the other one matches, so we replace else B is equals to x underscore tmp, right? And we go either way around to find out what's the solution of this one, this thing, okay? And then we will move on to find out the root of it. But we also have to plot this function just to see what's happening in here. So let's plot this function as well before we move on to do this, because this is like a, as you know that this includes sines and cosines. This is a function which has multiple roots. So we are going to find one root at a time, right? So that's why it's better to first plot it. So plt.plot. First, we are going to plot B. So let's say the x value, which is the v values in here, v vals equals to say a range minus say 1000 to plus 10, 5000 points. That's where we want to plot. Not a range, but sorry, it's within space. So let's plot v as x on the x-axis, and let's plot symmetric of v on the y-axis, and plt dot show. And we are going to, let's see, this is vval, sorry. Okay. So here we have some dips in here, and this clearly shows that we are hitting zeros at some points, right? And then there's negative values at some other. So let's have some values which are close. So let's not have such a large range, but have values which are close so that it's easier to visualize. So let's not go to minus 200, but let's go to minus 1000, but let's go to minus 100, right? So that will be here. And let's try to plot this once again. So yeah, you see there are multiple dips where it becomes negative. So let's try to look at this one first. So this is will be minus 30 or something. Okay, so we can also replace this in terms of energy. So let's write V in terms of energy because that units are better. So V is KL over 2 and root 2m E over H, right? So let's write K L over 2. So V vals is, let's see, V vals is K times L over 2, and L is nothing but the width of us for us. K times width by 2, and K is root 2 me over h bar as far as I can remember. This is root 2 me over h bar. Square root of 2 star m star E, it is energy over h bar. So let's have some energies which are, then the energy values are more realistic and we have a feel for it. So that's why I was trying to uh, do is something with energy. Okay, so we will have energy in electron volts for sure. So this will be energy in electron volts. So this will be NP dot Lin space. So we are going to have energy from say 0 to the depth of is 20 electron volts. So we'll have say something which is less than this. So we have 18 electron volts say, and we'll have 1000 data points star EV, right? This is mass. Okay, so let's try to plot it. Okay, so you see there are certain places where this dips, and we obviously have some other dip in here as well. So let's check very close by to this. So let's check at 2 electron volts perhaps, if that gives us a better estimate. Yeah, so it does give us a better estimate. So let's do the same thing for plotting the antisymmetric thing as well. This is same, right? So there are places where the asymmetric function also dips in here, right? So this is the root which is close to the symmetric dip, where you have some value, positive value, and then dips down, or this is the place where you have the antisymmetric dips in here, right? So this is what we are going to see what's happening. So let's then try to figure out and have this function in terms of energy, right? So let's see. Let's try to define F. It's then so we have to find out lambda energy. Let's call it E, such that we will call it with symmetric with the value of E in here. Right? You have to pass the value of E. So we know that energy will be in electron volts. So E times EV, sorry, this will convert your energy to electron volts, right? And then we know this. This is our K. So we are passing this as K. So, and for energy, we are going to replace this with electron volts. It's just energy which we replace to electron volts, the energy E in electron volts, right? So this is K times W times E. That's our U. So times W by 2. So that is our V. So we pass the V in here and we get the symmetric one. Okay. Similarly, we can do it for antisymmetric as well. And then we search for A. So let's look at the A value. So we give an A value of say 0.01, just some number, and then the other is say 0.75. So we know that there will be a root in between. So 0.75, right? And we are good to go. But before that, let's also plot this thing with a wider range and see what's happening. So let's do this for say 10 electron volts and see. You see there are multiple dips in here with 10 electron volts, and there are also multiple dips in here. So then let's go to 20 or 15, where you can see even more dips. Yeah, you see there are 1, 2, 3, 4, 5, 6, 6 dips till this, and these are the first 6 energy levels that we are going to find out. And one nice thing that happens for this quantum mechanical systems is that the symmetric and the antisymmetric functions, the roots of this, if you look at this, these roots alternate from the symmetric and antisymmetric. The symmetric one is the blue one, while the antisymmetric one is the orange. And you can see the places where these dips happen, where you go from positive to negative values, right, are the places where you see the function becoming very much changed, right? So this is what's happening. Well, so since you see there is a 10 to the power 7 hanging around here, we can also like normalize it by 10 to the power 7 just to have the values which are comparable. It just makes the plot better, nothing else. And play this, and you see this, the 10 to the 7 values are gone, and then you have this dips, and we are going to find out where this is happening through this false position method. Okay. So now let's try to see, after all these iterations, the values of A and B, either one of them is going to give you the position. So at the end, just to get an estimate, you get energy equals so as you know that A and B's are in electron volts, so the energy will also be in electron volts. So I just do an average. You can do anything. Either A or B is also fine. Okay, and let's print this. Let's use an F string and say E equals to 0.3F electron volts, right? That's the energy that we are trying to find. Okay, so it says there's a problem in here, and let's see what's the problem. It says that f of A and f of B are greater than 0. Why? So let's see. Then obviously your code is going to not behave properly. So let's say f of A is this, and let's say f of B, which is negative, right? So f of A times f of B is greater than 0 is what it says. Why does it say though? F of A times f of B, this is not greater than 0. So let's see. This would mean f of A times f of B is f of A. Okay, what's happening in here? Fs past the E, you have the K's, K times W by 2, and K is 2E over H bar, 2ME over H bar, and energy we pass in the value that we have. All right, so let's see. A f of 0. KW by 2 and K is 2ME. Okay. Let's see. Let's go back to 0.75 just for this specific problem that we are dealing with. And what we are going to do is stop this debugging and run the debugging once again. And fair enough, here something between 0.3 and 0.5, we can even do that. Say we have something like so at 0.3 and at 0.5, we are having functions which are of the same sign, right? So we have to choose somewhere in between. Okay, so somewhere the function is negative, right? So let's go through the function and try to find out the place where the function becomes negative, right? So for that, what we need to do is keep on finding the function, move from between 0.3 and 0.4, and find out the first place where the function is negative, right? So for that, let's see. Let us see. This is the values of a and b. Got it. So here in both cases, the function is positive. So obviously, we are not able to find. We will not be able to find the root for this. We have to find a place where the function is negative, and this is somewhere around here, and then we can optimize to find the root. Okay. So what we are going to do is we do like look at the range and find out the first negative quantity or something like that. So to np dot linspace from a to b. So this is like and we take 1,000 stuff and we find out the place where the function changes sign, right? And we do that by finding out f of the value of this function, right, between this. And then what we do is we do the place where this function f is greater than 0. You know the positive one, we want to find out the negative one, so we find out the minimum value, the function value that the function is minimum, right? So we do something like command C. We do something like this is, let's call this energy E test. E underscore test equals to command V. So get this function and then that just pass this to E test, right? So this will give me the values and then do something like B equals np dot arg mean. So this gives me the minimum value, the position of the minimum value, right? And then this is E underscore test, right? So this really gives me the function where I want, and closing the bracket. So let's see if this works or not. This is where I know that the function will be negative because here the function is positive and I have found the minimum value, so this is going to give me the negative value for this one. So let's save this and try to debug this code. Come in here and let's see what have I got. FA is a positive value. FB is a negative value for the function. So here I now clearly have a case where the function is either positive or negative. And now I can just iterate around and see what's happening and find out the place where this function kind of gives me value which makes sense. Okay, so do that. I come in here. Okay, so this I think gets changed. So let's see if this end the debugging, run this. Okay, it's taking forever, so there must be some problem with it. So let's try to figure that out. So this is fine. Then we just straight away move on to the while loop. Let's get to the variable explorer, remove everything that we have, and we are off to this. And here we are. We have the k values and things like these. Plots, we have obviously this plot, and we try to go in. So we come in here. Let's see, we have XGMP and difference. So let's see what we get for XGMP, which is 0.3, which is just using the two values, right? So let's see what we have for A. So we have 0.3 for A, and we have 0.37 for B. This is 0.3 and 0.37. We know that the root somewhere lies in here. So that was the idea, right? So we come in here. Let's see the diff. Diff is 0.07. So diff is, sorry, while diff is greater than tolerance, then we do the iterations when the difference is greater than the tolerance. If the difference is less than tolerance, then we obviously are fine. Okay, let's stop this once again. Let's come in here. So we have XGMP is something, and then f of XGMP is something, then f of A is also something, right? And f of B is negative. So we are now replacing then f of A with f of XGMP, right? So we go in, come in here, find out the next XGMP, right? And now we calculate the new difference. And now let's see, f of x, f of A now has to give me what I have got for f of XGMP previously. So this is what I have got for XGMP previously, and f of A has to give me that. Exactly. And now with XGMP, I get a new one. Yes, so I get a new value. So I come in here and keep on doing this. I guess, let's see, after like I went through a few iterations, what is the value of A that I have? Yeah, A is slowly marching, increasing. I see. And the diff is, so let's keep an eye on the value of diff that I have. And let's see if this is, diff is certainly decreasing, as I can see. And the value of this is increasing. So let me stop this one, run the code. Somewhere I get an invalid divide by invalid value encountered in divide. So which is for the simp one, which is in line 23. So this is much before that I get this one. Okay. So I see, I think this is not a problem in here, but problem in this one. So let's, in this plot, try to have functions which are extremely close. Value which is And let's have A to be the one where we have just flipping over. So that would be something which is greater than 0, right? So this is B and A should be E test. Let's have A which is even close, say 0.36, and try to see what's happening in here. Okay, and let's print the def. print, and okay, and iterations is increasing. Iterations, okay, plus equals to 1. So I have forgotten to increase the iterations. And let's do this. And let's print iterations and the value of xtmp. Say iterations is less than max iter. This is not or, but this is and. So let's see what's happening to our diff. Why is it just going to, because I think we have converged to 0.37. Okay, so A and B's are not changing or what? Okay, so I think this is wrong because XTMP previously and now is changing. So yeah, X underscore TMP old is equals to X underscore TMP. And now the difference will be X underscore TMP minus X underscore TMP old, right? And this will be np.abs, absolute value of this. So this is how and the first XTMP will be is equals to, just to start with, some value 0. So it's just very large, right? And now you come in here, you do XTMP equals to XTMP old, and then you find out the new XTMP, right? And then you calculate the difference. Okay, so let's see. Okay, so we have converged very quickly. In just 2 iterations, we were able to converge. Say, let's now change this 0.36 to something else. Let's change this A, right? 0.1. And are we able to converge? Yes, we are able to converge this to 0.238. I guess there is another solution close to that 0.238. So then if we try to find out if there is something regarding close to that, we can just do something like 0.3. A is 1.1 and B is this. So let's see if there is something between 0.1 and 0.3. So 0 and 0.3. Yes, there is a place where this problem. 0.5. Let's see. Yes, there seems to be something where between 0.3 and 0.5, and this is exactly the loop this solution is giving. So let's plot it between 0.3 and 0.5. So let's see, 0.3 and 0.5 is the other one, right? Yeah, so, and this is roughly around 0.338 is what we are getting. Okay. So this, I think, is the lowest energy level that we have got from this solution. And we are pretty close. That the difference is also pretty close. So we can, for now, take this out of the print statement. So we have got E, and then we can keep on doing this, just changing the brackets to different values, and that is going to show up in the plot. So we do this to 5 electron volts till 15 electron volts, say. So we have all this. And let's try to do one thing for the antisymmetric as well. Let's try something between 4 and 8 for the antisymmetric and see what's happens in here. So between 4, we try to find out the orange root in here, and 8. Okay, so this is around 6. So we do 5.5 to 6.5 in here. So we do a 5.5 and 6.5 in here, and change this one. That is the other one, yeah, to asymmetric, so that we are trying to find out the orange roots. And try this. Yeah, we did. You see, we get 5.758, which is very close to this thing that you see. So clearly, this gives you one root for the orange. So this is for the antisymmetric part of the wave function. The other one, where you have the cosec square instead of the cos square, right? So this seems to be working very well. So the idea here is now just find out the depths, go one at a time, and go through all the first 6 energy levels. So you'll know where the depths are and just find out the energies, which is exactly what we are doing in here. So if you go back to this one, we'll probably see some of the values and the iterations that we get from this. Okay. So I think this one is quite a bit of challenging, but you get the rough idea of what we want to do. So next we can go to the roots of a polynomial. But before we go there, I would ask you to please ask if there are any questions in here with this. Okay, assuming that there are no questions, then I straight away move on to the next one, where just a minute. Yep. Where we are trying to find out the root of a polynomial, right? So there is no general formula for the roots of a sixth order polynomial, but one can easily find them using a computer. From x equals to 0 to x equals to 1, make a plot of the polynomial that's given, and by inspecting it, find rough values of the 6 roots of the polynomial. So let me open the question once, just to people to see. Not this one, but this one. Yep. So you see, consider the sixth order polynomial is this. There is no general formula for the roots of a sixth order polynomial, but one can find them easily enough using a computer. Make a plot of p of x from x equals to 0 to x equals to 1. And by inspecting it, find the rough values of the 6 roots of the polynomial. The points at which the function is 0 is exactly the root of the polynomial. So let's code this polynomial up, and then we can move plotting. The first part, I think, by now will be very straightforward to you. Okay, so lambda x. So let's call this polynomial LMED lambda x, such that the polynomial is 92 times x to the power 6 plus 2772 x to the power 5, 2772 times x to the power of 5 plus, sorry, it's a minus 2772 times x to the power 5 plus 3150 times x to the power of 4 minus 1680 times x cubed plus 420x squared plus 420 x squared minus 42x plus 1, 42 times x plus 1. This is fairly long polynomial, and now we have x vowels. MP dot. I mean, you can, for example, even plot this in Desmos just to check, but yeah, we will do that as well. From 0 to 1, say we take 1,000 points, data points, then we do plt dot plot just the polynomial. So this will be x vowels whole of and then plt dot show. and you see the polynomial that is in here. And there must be some roots that we can get from this polynomial. 0 to x equal to 1, and we're going to find the rough values of the 6 roots of the polynomial. Let's see. There is a 924, which I missed in here. X cubed minus 277 to x to the power 5 plus 3150. Okay. Yep. So here it is. We see the polynomial, and here you can see that if we pass this to x equals to 0, there are 1, 2. So let's have a line as well. PLT dot H line. I think it's called. You give an x mean and x max and y value. So we want it at y equals to 0 from x equals to 0 to x equals to 1. And we want this color to be, say, black, and line style to be dotted. Okay. So as you can see in here, if you pass the line through x equals to 0, there is 1, 2, 3, 4, 5, 6. 6 values within which 1, 2, 3, 4, 5, 6. Yeah, 6 values within which the function crosses. So these are all the roots of the polynomial, right? And now we are going to find out the values of these roots using Newton-Raphson method. Depending on where you are starting, you will be converging to one of these roots. Okay, so let's try to do that. Let's write a function def. So Newton-Raphson method will be, again, we will have something like iterations, which is 0, and max iter, which is, let's say, have 5,000, and tolerance is 1.0 e minus 0.6 is the tolerance. So now that I do while, and we have a definite difference, DIFF is equals to NP dot INF, it's infinite. Right, now they do a while def is greater than tolerance, and iterations is less than max iter, right? And we call in here, we do iterations plus equals 1 x underscore TMP. So temporary, the value which we get is something, say, just to dummy with this 0. Right? And then we have something like x underscore TMP underscore old is equals to x underscore TMP. This is almost the same as what we were doing previously, except that the formula will be different. We were using regular falsy paper in the previous question. Now we are using the Newton-Raphson one. Hey, so let's see. Here, what we want is a derivative. So the derivative of this polynomial, d lambda x. The derivative is also pretty simple. We do a 924 times 6. So this is just differentiate a polynomial times 6, which is 5544. And these are like crazy numbers, but anyways, times x to the power of 5. This is a fifth order polynomial because when you differentiate it, you decrease by 1 order. Then you do a 2772 times 5 times 5. So let's put this in here. This times x to the power of 4 plus 3150 times 4. 0 times 4. This gives you 12,600. 600 times x cube minus 1680 times 3 times 3. This is 5040 times x squared plus 420 times 2 is 840. So they give it 840 times x, right? And a minus of 42. And for last one is the derivative is 0. So, okay. The Newton-Raphson method requires you to have the derivative of function. So that's why we calculated the derivative, which was analytically available previously in the case of the the black body problem. Analytically, the derivative was too complicated. So we use the numerical method. But since this is a very simple polynomial, we can well put the analytic value. Right now, def is equals to ABS x underscore TMP minus x underscore old. Right. And let's find out xTMP. The new value of xTMP is nothing but x underscore TMP minus whole of x underscore TMP divided by whole curve of x underscore TMP. So this gives me the new value. Go through the one more iteration and try to converge, right? And this is the initial guess that you have. And the first guess will be 0. So we are at 0 and we try to move in, right? So, yep. And let's, after this, print x underscore TMP, right? And x equals to 0.3 f. Let's see this one and make this an f string. Okay, and print this. So 0.034 is the first one, which we converge to. And then let's try something like 0.2, and hopefully we'll converge to the next one. 0.169 is the next root. Let's try 0.4. So 0.381. The other one, let's try 0.6. I think it's a bit more than 0.6, the next root. So it's the first root, the second root, the third root, 0.6. 0.619, got the second root. Then we'll try 0.8 to get the next root. 0.8 is going to 0.831, get the next root, and we can try 1, which will get the last root. 0.966. So we got the last root. Okay. So the nice thing about Newton-Raphson is that you do not need two values, but just one value, and that is good enough for you to guess what the solution is, right? And this is how this works. So I hope that this is clear. If not, then please ask. This was fairly a simple problem, in my opinion, compared to what we were doing from previously. If this is done, then we can just move on to the last question, which we can try today. My laptop is just running out of power, so what I'll do is I'll connect this to for now. So I hope that this is clear. Then let's move on to the last question that we will be trying today, and then we can call it a day. And this was, I guess, the final session of this course. We were not able to cover a lot of stuffs, but we were able to cover whatever things that we have gone through pretty much in depth, and were able to discuss a lot of questions. And these were like really real world problems, not some problems which are typically made for some particular demonstration. Such problems were also there, but they are pretty limited. For example, one of such problem is this one, but the most of the other problems are real world problems. So while solving those problems, we also came across some of the challenges which you would most likely be facing when you are doing computational physics to solve real world problems, and not the ones which we would generally have when we are doing something when we are trying to solve problems which are tailor-made for one particular kind of algorithm, right? Okay, so let's look at the next question. Here, a minute, if I see, let's see if I have a charger or not. Yeah, I think I have. I might have just left my charger back at home, but okay. I hope this charges my laptop. Yeah, it does. Uh, yeah, so let's see. There is a magical point between the Earth and the Moon called the L1 Lagrange point, at which a satellite will orbit the Earth in perfect synchrony with the Moon, staying always in between the two. This works because the inward pull of the Earth and the outward pull of the Moon combine to create exactly the needed centripetal force that keeps the satellite in its orbit. Here's the setup. So here you can see this is the satellite. So the Earth is pulling it to the left, while the Moon is pulling it to the right because of attraction. And L1 point is this particular special point where the both of this pull balances each other, right? And then this when these balances the centripetal force, so that the satellite the net force between the Earth and the Moon so balances the centripetal force. I'm sorry, not just balances each other, but balances the centripetal force. So, and then the Moon can stay in this orbit, and which is very stable in such an orbit. So assuming circular orbits, find the distance r from the center of the Earth to the L1 point. Write a program that uses the second method to solve the distance r from the L1 point and compute at least 4 significant places. So let's see what the second method is. So second method. Okay. And here again, this is like, let me get rid of these. Got it. Yeah. Second method is like, again, we have to look at the roots, and then we try to find out like a guess value, and then we recursively go on to find out the new value, right? And the idea here is that we draw lines. That's why these are called seconds, and try to find out the value based on that. This is very similar to Newton-Raphson, except the thing that we do not need to derive it. Okay, so now we'll derive the formula for second method. So let's see. Is also a recursive method for finding the root of polynomials by successive approximation. It's similar to regular falsy, but we don't need to check for fx1, fx2 less than 0, and again after every approximation, right? In this method, the neighborhood roots are approximated by the second line or chord of the function x. I think I need to get rid of this distracting ads, but I don't know how I'll do that. Anyways, so let's not use this website. It's too distracting. But anyways, the ads are gone. Okay, I think we are fine. That case. Let's see what Wikipedia tells. So here, for example, is the second method where we try to find out the approximation for your root. So you say you start with x1 and x2 is your approximation. So let's see. Let's see if there are a better derivation. Starting with the values x0 and x1, we construct a line through, okay. So you see, you start with x0 and x1, where again, where the thing is, opposite sign. So x0 and x1 are opposite sign. And then you draw a line which passes through this, as shown in the picture above, right? In the slope intercept form, the equation of this line is this. Yeah, just like what we were doing for regular falsy, right? The root finding of this linear function is the value such that x equals to 0. So as you move closer and closer, then the straight line becomes a good approximation of the function in here. And the curvature of the function doesn't matter once you're pretty close. So we use a new value of x2 and repeat the process, right? We continue, okay. We will use this, and then we ask where this line cuts the x axis, and then that is the approximate root that we want to find out, right? We use this new value of x2 and repeat the process using x1, x2 instead of x0 and x1. We continue this process of solving for x3, x4. Use this new root, new value of x2 and repeat the process using x1 and x2 instead of x0 and x1. Okay, so we repeat the process with, again, find the function in here and repeat the process for x0 and x2 instead of, so we repeat this process using x1 and x2. x1 and x2, so that if you repeat the process, then that will give you coming in here instead of, yeah, x0 and x1, right? So now how do you choose which one to replace is the question. So let's see. X0 and x1, we continue this process solving for x3 and x4 until we are with sufficiently high level of precision, right? So you see your x2 is x1 times this, and then your x3 is x2 minus. So this is recursively going on, right? And then you keep on replacing this. And this is the Newton-Raphson one for sure. Yeah. Okay, so let's try to use this method for a specific problem. But for that, before that, we just put in the gravitational constants and the constants that we have in here, 6.67. This will be really helpful. 674 e minus 11. M is 5.974 e plus 24. Small m is 7.38 E22, 38 E plus 22. RS 3.844 E plus 0.8, and omega is 2.622, sorry, 2.662 E minus 0.6. Done. And then after this, let me try to find out the charge at once. If that is possible. I'll be back. I think I cannot find it, but if I'm not able to continue because of the charge, then I'll let you know. I'll resume once I move away from my office and get a charger. Okay. And then we are going to find out the omega and the radius. For that, let's move and tell you the formula which we are trying to solve in here. Yeah. You see, this is the formula which we are trying to solve. So we have G So this is M plus is Earth and MS is a satellite. So this is the gravitational force from the Earth to the satellite. This is the gravitational force from the moon to the satellite. And this is the centripetal force on the satellite. So these three terms balance. So if you try to solve this, you see you can cancel out the MS. And this is the equation that we are trying to solve, right? R is the radius of the Earth, right? And then small r is what we are going to solve it, right? So you have r on one side, which is the distance between the Earth and the satellite, and the distance between the moon and the satellite is capital R minus small r, where the uppercase R or capital R is the distance between the Earth and the moon, right? So let's do this. And I think the natural unit for all these distances is AU, or astronomical unit. So let's see, AU to meters is this one. So it just becomes easier if you use the natural units where quantities are order one. It's numerically better. And the computer will thank you for doing something like that. Okay, so something like this. And let me also okay. And then let's go in here. And I think here. So I would say to please bear with me. And if the class ends because my laptop is dying and I do not have the charge left, I will try to resume in about 15-20 minutes. I go back from my office to my home and then I resume back. Yeah. Okay, so this is AU, and then we try to solve for the equation, right? So we have depth, distance. We try to solve for red is what we try to solve. And let's see, which is GM minus GM over R square. So GM over R square. So we do return minus G star. This is M over rad star plus GM moon over R minus small r square. G times M moon divided by uppercase R minus rad square. And then this is minus omega square R minus omega star 2 times rad. Is that what we want to find out, right? And let's see. I am going to copy some stuff from this one, which will make it easy for me. Okay, so this makes it easy, and then just find out what's the temp thing, right? So yeah. So for this method, it is f of xn plus 1 and we try two different rads. So let's call it x1, x2, right? So x1 is, say, radius of the Earth itself, r. So it's 0.01 times r, something like this, to x2 is r. So it's very close and very far. So 2 points which we have taken, right? And then x underscore old is equals to x underscore old is something 0. Yeah, just for the sake of it. And xtmp old, sorry. xtmp is just 0, right? And now we are doing an xn minus, here this is going to change. So xtmp is xtmp, the previous one. So we have xtmp1 and xtmp2, and xtmp is new one. So xtmp old 1 is xtmp1, and x underscore tmp old 2 is xtmp2, right? These are the two things that we are going to have. So let's see, xtmp is xtmp, say, 1 minus, let's call this distance. So we have this distance of x tmp1 times you have xn, so xn is xtmp minus xtmp2 divided by just pass this as distance. I'm trying to hurry up in here just because of my charge on the laptop, and I apologize for that. Okay, so XTMP1. XTMP old 1 and XTMP old 2. XTMP is XTMP1 minus this, and this is XTMP2. Is going to be this. So where is X underscore TMP? Okay, so this is it. And then difference is the XTMP1 minus XTMP old 1. Old 2, and I mean, anyone will do. So, yeah. Let's see if we are able to get it or not. And then we can print distance, an F string of XTMP 2.4F, this by AU. So we have an astronomical unit. Okay, so we have a division by 0. Why is that so? So let's print as usual. We are going to print iterations difference XTMP1 and XTMP2. Let's see. And the very first thing, we get an error, so we'll just go in here, try to look at what's happening. X underscore TMP, do we have anything like that in here? No, so we can get rid of this one. And try to do this. Yeah, let's move. Okay, first let's get rid of the variables. Yes, got it. So come in here, and okay, what is happening in AU? So okay, that's this one, stop, and this one again. Okay, so now I think we're fine. We move it here, move on iteration, XTMP old 1 is something, XTMP old 2. So we got two values to represent. And here we have, let's see, for XTMP old one and XTMP old two, we have this. So let's see, let's do so XTMP distance XTMP1 would give me something. XTMP2 gives me an error, and that is because I guess I put this to R, so I'll put this to 0.95 of R. Exactly at R, there is a problem with this function. As you can see, it blows up, so it cannot have it. So let's top this, say this one, and fair enough. We see that 0.0024. This is in AU. And then now we can get rid of the print statement. So the only problem was this 0.5R. Okay, so you see that 0.0024 AU. And this is the Lagrange distance of the Lagrange point. If you search, L1 point from Earth distance. This is about this much miles. Okay, so let's and this is miles to AU, which is an astronomical unit. And let's see, it's yeah, I guess I'm doing some error because I'm being in a hurry, but you see the right answer should be around 0.002 AU, which I had done many years ago, and this is exactly what I get in here. It's 0.0024 AU. So this solves the problem. And the idea here is that we use the second method and started with some guess and then tried to converge to the solution using the second method. So this is the end of today's class, and I hope this was useful and beneficial. And we were extensively covering different kinds of ways in this class for solving transcendental equations, and most of these equations from real life problems. So there were many challenges which are not usually that you would get when you solve problems which are just tailor-made for some demonstration of a procedure. But this is something which you are repeatedly going to encounter if you are working on computational physics in future. So hope this was helpful to you in that sense, and it helps you move along. And on that note, I'll stop sharing my screen and I'll end today's session. Have a nice day and all the best for future.